doesn't really settle down until basically a few months before we ship on there. With this, we've got a long period of stability to the point where we already are working with some licensees on the technology, even though we're still a little ways from shipping things. The core components, especially the media creation aspects, have been nice and stable for a while now. So it is becoming more and more of a designer's and content creator's task right now. So at that point, I've still got work that I'm doing on optimization. There'll be a few more features that are coming in. But some of the things that I am starting to think about now are where we're going to be going from here. And the horizon on all of this is always quite a ways off. I mean, Doom is based around the technology that was made available with GeForce One level hardware. And this is a constant problem in the computer games, graphics, and games industry, is that you need new capabilities from the hardware to design something, but by the time the software comes out that really takes advantage of that, usually people don't even have that original hardware anymore. And I'd actually like to see a show of hands. Who here has an original GeForce One 256 that they still use as their primary gaming platform? Very small number of people. So the features that were announced at that level, the original GeForce, the original Radeon, that was the feature spec that Doom is built around. And the key things that we needed there were 32-bit color acceptable for everything, 32-bit depth buffer width, or 24-bit depth, 8-bit stencil. Those features have been present in higher-end cards for a while, but the neat graphics things that added the capabilities that we've got were the Doc-free blending and the cube maps. So that hardware, when it first came out, enabled the type of technology that Doom has become on here on the graphics side. But here we are, by the time we're actually done with that, almost nobody in our core hardcore audience is going to be using those original cards. They'll already have upgraded past that many times over. So as we're looking forward, the next generation of technology is going to be based around the graphics technology that's just becoming available with basically the Radeon 9700 and the upcoming NV30 hardware. And the key differentiations that we've got with that are floating point pixel formats, fully generalized dynamic texture lookups inside there, and of course much larger spaces, faster memories, all that going on. There's actually one intermediate step that I sort of wish we could have had benefit from, but it's just not working out schedule-wise. The current generation of the 8000 series Radeons and the NV20s added some hardware that would be useful in our game engine, and that would be the ability to do basically really good ambient diffuse lighting, where what we've got right now is all directed lighting, and it works great for doing dramatic things, but it's not the most natural thing in the world for the way the lighting works, say, outside. I mean, not that any other game is doing a particularly better job than any of that, but it's not the lighting. And we have a few tweaks in the lighting where we have an ambient light that kind of shines light forward onto all the bumps to let you kind of brighten everything up without giving it a real directed look to it. But what you really want to do with that is have each bump look up in a cube map, so it knows that, okay, the bump's looking up in the sky are blue, and the bump's looking down or red in our case, the bump's looking down at the ground or darker, and to be able to do that on a per pixel level. And unfortunately, that's something that's just not possible on first generation 7500 GeForce 1-2 class cards. And while I would consider adding features like that to the current things, we're such an art and media-driven kind of process now that you can't really spruce up and change the way ambient lighting works on some cards and expect it to be something that the designers are happy with, showing without it on the other ones, because it can make a fairly big difference on how it looks. So that's one of the things that that I really want to be improving. But one of the most exciting thing for me as a graphics developer will be moving towards the higher color depths and the more general flexibility there. And it's been kind of amusing for me watching general reactions from the public. It's pretty funny seeing a lot of people going on about why on earth would we need 64-bit color, let alone 128-bit color. And you could practically word for word take some of these appalled comments about this and translate back a few years to the 32-bit color stuff. I mean, everyone remembers the whole argument about 16-bit color is good enough. Why would you want to go half the speed to get 32-bit color? And it's, in retrospect, it's a foregone obvious conclusion. So people are taking some of the wrong things from the 64-bit color question on there, because people will rightly say, well, a monitor only has about 32 bits of resolution. You've got about 10 bits color components on the red, green, and blue. But that kind of misses the important point about why these new features are going to make a really big difference on there. While a monitor may only display this, say, 10-bit resolution on there, the human eye is capable of perceiving well over a range of 64,000, well over. The difference between like these lights that are shining right in my eye here and the floor sitting down there in between the aisles there, that's a difference of hundreds of thousands of levels there. And while the monitor, if we took a direct digital image of my point of view here, would not be able to accurately represent the spotlights and the dim floor there, there's good reasons for why the graphics engine should be calculating things directly like that. In fact, in a lot of ways, the way we've been doing colors and graphics is not a particularly good way. These monitors have this gamma-corrected curve on them, and we're doing all these operations like adding and multiplying that are actually not really correct in gamma-corrected space. But we punt on the issue a lot where, okay, multiplying it down makes it darker, maybe it's not the right darkness curve, but there's such a huge variance in monitors already. That's one of the favorite bitches of our artists, is that things look different on their monitors versus everybody else's monitors. And it's a tough problem to solve there until we can get calibrated monitors for everybody. There's only so much that you can do by asking people to tune and correct different things on color calibration cards or noir patterns or anything like that. So it's at least justifiable to punt on a lot of that, but there's going to be a lot of neat things that we can do as we start doing things more correctly. The way you should be calculating all graphics, the way it ought to be done is you're basically counting up photons that are incident on a surface. Lights spray out a whole lot of photons, they're collected on surfaces. If you're doing things really right, you've got an inverse square fall off, and you've got radiosity balances and all of this. So what we want to do is do all of this calculation the right way. And then we know at the end it's going to be going on to some not exactly optimal solution that we want on the monitors there. But there's still a lot of benefit to be gained by doing all the intermediate calculations the way you really should do it. And to some degree, game development, especially real-time game graphics, has always been about how you approximate doing what you really want to be doing. But it is useful for everybody to recognize that we're just approximating what we really want to do. And when technology comes along that lets us do the right thing instead of whatever crappy approximation we've been doing, we really should be excited about it because it's more right, and we'll get a lot of benefits that aren't immediately obvious from it. The things that we'll get notably from the increased color range, and this is one of the things that I think a lot of people that are skeptical about it right now would be surprised at how easy it is to reach some significant benefits from the high dynamic ranges on there. One of the obvious things that games, the entire generation of hardware accelerated games from from Quake on up, everything has sort of a dimmed look to it, where since almost everything is done by multiplying things by fractions, the artists draw texture that they think may look pretty good, and then it gets dimmed down as it gets further away from the light, it gets dimmed down as it's turned more obliquely from the light, or it gets dimmed down when it's in shadows partially. So you're just dimming and dimming and dimming this original thing. And that's been a constant struggle really with a lot of the artists to get things bright up originally, because it's natural to draw something so it looks good in whatever the situation that you're looking at it on. You've got your view in your mind's eye of how this should look in an appropriate setting. And what you really need to do if you're only going to be dimming down these textures is you need to try and envision this surface lit under arc spotlights or something so that it's extremely bright, but then it doesn't look the way people picture it in their imagination. So games have been kind of crunching around some of this by doing various techniques like doubling up the multiply value when you're blending the light maps, but then that would carry over to the characters. Doom has a more generally flexible system, even though it's still inside the limits of 8-bit per component rendering. It does allow you to specify lights that are much brighter than the normal range. We don't use this all that much yet. Some of it's, I'm still pestering the designers to try and put some of it in some places, but the downside is that without a good sense of reflected lighting, without any kind of radiosity bounces on there, it does tend to make the edges a lot more harsh. But in a few cases where we have had some brighter than normal lights on there, it does give it a more realistic feel. But once you've got, I have to go through some interesting software arrangements to go ahead and make all of that work inside the space of our current generation of rendering technology. But the next generation stuff, all you're going to have to do is basically say, this light is arbitrarily bright and everything just kind of magically works. Everything multiplies together, turns out to be the right thing. And then one of the hot technologies for gaming with the new technology, new rendering technologies, will be bringing a lot of the research that's been done on tone mapping into computer games. Because again, we come back to the problem of, in a typical game level where you've got something interesting, outdoor area and indoor area, you may have this outdoor area which is literally 1,000 times brighter than some internal dark closet that you've got, but your monitor's only got this, this range that it's always had on there. So figuring out how to go ahead and calculate the right thing, have this incredibly bright sun shining down versus this tiny little night light in some room, calculate those values right, and then get them put up onto the monitor in such a way that one area looks dim and the other looks really bright. And there has been a fair amount of academic research on this, which is very rapidly going to become applicable to games here, where there's different things that you can do to the way the colors are processed. Like as lights get really dim, because of the way our eye operates, you tend to lose color fidelity and things start looking more grayscale in the eye. And you just get a more black and white image as the lights get dim, while the colors saturate much more in the really bright areas. And then there's the whole concept of light flares, which I've got two of them right in my eyes here, which we've been hacking in games for a long time now, by basically taking this bright, a fall-off flare that the artist draw and just kind of plastering it up on the light and doing various contortions to it to make it sort of act the way the light does, where we bend the polygons around, we stretch them into different things and try and make them fade out as they get occluded. But what's really the right way, again, to do these types of things is the light flares that you see are actually, there's two types of light flares. The one that you see in a foggy night, say, when you've got a street lamp and it's foggy at night, that's actually light reflecting off of the little particles, the suspended water droplets there. And that is actually reasonably accurate to model by having an alpha-blended model around there. But the ones that people think of more commonly, the really bright lights and the halos and effects around them, those are actually ocular effects, where they happen inside your eye, and which is why you can test that to see which type of flare something is. If you close one eye and move an occluder like your finger over the exact light, if it's a fog light of some kind, you'll still see kind of a flare around it. But if it's an ocular effect, as soon as the actual bright spot is removed, all of the effects go away around it. So we have a way with high dynamic range things to simulate this this accurately, where the correct way of doing all of that is to render your entire scene in exactly the way the way it should, the way it collects light, where light sources are just rendered as extremely high photon value surfaces. And then when you're all done with that, you go ahead and take the entire screen and you kind of blur it all down, and then everywhere that there was a bright pixel, a really bright pixel, it generates a halo around the pixels surrounding it. In the simplest way, if you had infinite hardware resources, you would just scan over every pixel, and for every one that's above a certain value, you put this kind of blur around all that and let all of them add up to be the effect that you want on there. Realistically, we're going to go ahead and downsample the screen a few times, and there'll be a little bit of coarseness to it. But doing things that way winds up getting a whole lot of other interesting effects from there. It's not just the flares around the lights. One of the things that some games have done recently was started adding flares around specular reflections. You've got bright light shining onto cars, things like that. And it's the same basic thing, where you've got a surface there which is having an intensity so much higher than everything else around it. It's the same thing for light. All the light is a filament that has an extremely high intensity coming off of it. Everything else is just kind of smeared together there. And when you've got bright car bodies, say, under a sunlight, you've got the same thing where the sun is hitting the car so brightly that the reflection along the specular vector is actually bright enough to cause ocular effects. Now, you can do this you can set up a kind of special case way of doing that by just checking every vertex, seeing if it's bright enough, and throwing a flare on top of it. But again, the right way to do it is to just draw the scene normally, where some of these pixels are going to get way out of range values, and then you do this post-processing step where everything just automatically flares there. And that type of consistency those are the types of things that I like looking into the graphics technology side of things, where it's, a lot of times you'll get a lot of mileage out of hacks and presentations that achieve the effect that you want for people, but have to be kind of carefully protected in some ways, where there's a lot of graphics effects that are reasonably cheap but break down if they're not confined to fairly special arrangements. And I've always avoided these in the engines that I've done. Sometimes I'm probably a little bit too aggressive in that, where there's a lot of times when throwing in cheap hacks sometimes is the right thing to do. But I feel a lot better about it when we have a generalized, consistent way of doing things. And Doom has been the best example of anything we've gotten so far about that, where everything really does kind of hang together in a consistent way. And any cleverness that's going on is in optimizing things that don't affect the actual output. The output is the same. We're just trying to optimize the generation of that. But so things like we do have flares in Doom, and they are done in kind of a hacky way. I mean, in some ways it was better than what we had in previous games, where they actually come from areas. They're not just point flares. We can do some interesting things with the shaped lights and the way the flares go off of that. But it's not really what I want to do. And if anything, that type of stuff goes in grudgingly, where I can recognize that the game would look a lot cleaner without it, but it's not the type of graphics effect that kind of works seamlessly in all cases. They still have to worry about kind of different problem cases with it. And that's the type of thing that with high color depth stuff, we're going to be able to make just go away. And the other set of things that's going to be changing with the advancement to the next generation graphics technology is that right now we're still in a matter where all of the existing cards that do this program forward, we have like 6 different semi-specialized backends to take advantage of the features of different cards. We have one fallback kind of standard path that people implement the ARM extensions they can run on this, but they don't get the highest performance with respect to their highlights thing. So it's been worth my time to customize things for the different cards. But it puts me in an interesting position of really recognizing how tedious it is to try and get even the major high points of each of these cards using their abilities here. So right now we have Indy 10, Indy 20, Indy 30 backend, the standard backend. We've got an R200 backend that's currently supporting the 8700 and 3500, 9500 ATI cards. There's some pressure to go ahead and specialize that yet more to take some more advantage of the newer things. And then we've got backends for 3D Labs, potentially Matrox and SIS, and we'll see how the rest of those go along. But it's a real pain to just go ahead and try and take advantage of the features of each of these. And it's not a matter of something that even an API could have, a common API could have addressed on these, because the truth is they actually have different capabilities. It's not that I have to use 2 different extensions just because the developers or the hardware vendors are being willful about it. It's the difference between a 2-texture card with robust combiner logic versus a basic 2-texture card, a basic 3-texture card, 4-texture card, 6-texture card. There's actually different requirements for that. And Doom has taken a fairly conservative approach to just kind of keep my sanity on tracking all of these problems on the different cards, in that almost all the rendering takes place through the standard path, all the basic things about GUI surfaces, rendering of special effects. Most of these things are exactly the same on all cards. And the core place where the optimization takes place is at the surface light interaction level. And this is where each card there's a lot of pressure to try and make each card run a little bit better on there. They've got one little tweak that can save one rendering pass, where it takes 5 passes on, say, a 2-texture card, 2 or 3 passes on a 3-texture card, 1 pass on a 6-texture card, and these wind up being different programs. They just have to kind of sit down and write them. You have to write the vertex programs which feed them appropriately for all that. And it's difficult to see, and this is with a very minimal spec. Doom was specifically kind of set up to make this as easy as possible by only having this one path, where it degenerates all the complex things. Like, there's not a whole lot of examples in the demos that we've shown, but we have some surfaces that are really complex that have multiple scrolling overlays with multiple scrolling lights that affect them. And so high-level code decomposes this into kind of this basic primitive there. So already we're not taking maximum advantage in all cases of existing hardware. Like when we've got a light that's actually composed of two overlaps that move relative to each other, it's possible to write more specialized code that gets that done in, say, 2/3 the time of doing it as two separate lights. But then that would require all this extra work on all the different cards, and we'd wind up just with a lot more problems there. So we kind of punt a little bit on the performance case there to kind of keep things more manageable in that case. And that really leads to the way the graphics, APIs, and hardware stuff needs to evolve to make things reasonable for us to do this in more complex cases. Because it just would not be reasonable to make maximum advantage of a half dozen cards at one time. It would just be too much to track if you wanted to really be aggressive with doing lots of things with the shaders. So what we really need is an API that allows us to specify what we want to have done, and then the driver can, as it needs to, cut it down into multiple passes in different cases. And that's another thing that a lot of game developers have a visceral negative reaction to. It's just you can see people, retreating in revulsion at the concept in a lot of cases, and that's because most software developers have had the experience of having something fall down a software accelerated path, where all of a sudden your game is going around at 30 frames per second, and then it drops to 1 frame every 3 seconds because you enabled something that fell down a software emulation path. And that's what's set a lot of people's minds about why this is a really bad thing, why things should only be what's fully accelerated by the hardware. But when we're left with that type of thing, then you're left with the situation that we have right now, where we have to identify exactly what the capabilities of the hardware are, and we have to customize our logic for each of the pieces of the hardware. What needs to be happening, and this is something this is one of my soapbox pieces here, because I don't have complete buy-in from the industry on this yet, although I feel like I can make a really compelling case for it. We need to have an API that allows us to specify an arbitrary, without limits, shading program, and then the hardware needs to have the freedom to decompose that into whatever it needs to get the job done. And there's some hardware that will help with doing this, but even today, if I wrote the Doom 3 kind of general light interaction shader, an automatic decomposition of that process into a dual texture card would not look very different at all from what I actually did by hand. The theory that an automatic decomposition is going to be radically slower than what a programmer would do. There's a little bit of programmer's ego there that gets in, and you just think it's like, well, some automatic process is never going to be as clever as I am. But this is the same argument for people that have been around for a while that people were making in the transition from assembly language to C programming. This was the time frame of when we wrote the original Doom, there were a lot of games that were still developed completely in assembly language. And they would make the same arguments about, and also against virtual memory. I mean, all of these things have been big advances in development. You always have people that will sit there and grump about how, this is going to impact performance in different ways. And there will be cases where you look at it and say, yes, you could have done this better. You can see that with compilers now when you open it up and you're like, why the hell did the compiler do that? But for the most part, what people don't, the people that are making those arguments miss about that is you can concentrate at the micro level there and say, okay, this instruction sequence, this statement, I would have done this better. What you miss is the higher level optimizations. And like I said with Doom, there's performance there that I know is on the table that I just cannot take because it would require too much complexity in testing. Where if we had one common destination target for things, it would be worthwhile to go ahead and say, all right, here's a special case for a scrolling surface with no ambient light. There's a special case for a surface that has no specular map. Because like right now, in the rare cases when we specialize things like that, instead of having a case for surface with no specular map, surface with no bump map, it actually assigns a default texture to it, where it can clearly write a more efficient one, where it says, all right, we just don't need to do this. Now it's multiplying by 0, or multiplying by 1, or doing whatever it needs to kind of make an identity case. So when we get this type of interface that will allow us to just kind of write what we want once, and then have it decomposed as necessary, that's going to make a big difference to how the process of development works. It's not obvious necessarily to everyone right now. It's still working in more of the single pass type rendering arrangements when you're trying to go really fast. But Doom's basic path right now is 5 texture passes, 5 passes with 9 textures on a dual texture card, decomposed down to eventually 1 pass with 7 texture accesses on the highest end cards, which are ATIs right now. So there's already a lot of this decomposition going on. It's just a question of whether it's programmer done or done behind your back in the API. There's a few picky technical issues about exactly like how you can have invariance with the decomposition in various ways, but I'm really 100% convinced that it's the right direction to be going, and I've been on record as saying that the next game engine that I work on after Doom here is going to be written in a high-level shading language. There's just no doubt about it. There's not going to be custom per card assembly specifications going on there. It's going to be at a high-level language, and the drivers are just going to have to deal with it there. And they do a really bad job. And so what this lets us get is that it future-proofs the hardware, where you can write something. In fact, developers should start writing things that take multiple passes. And I think Doom's a good example of this. I had a bunch of hardware people tell me early on that I was the only developer that they were talking to that was looking at doing something with lots of passes on the slower cards and less passes on the more modern cards, that all the other developers were basically cut features on the slower cards rather than making the faster cards go faster. And there's some merit in that point of view if you're trying to maintain the constant frame rate on as the cards go down. My point of view is that it's better to keep the quality the same and scale resolution. It means you've got a really slow card. It's better to have exactly the same pixel paths that are tested and will have the same visual fidelity and just drop the resolution way down. So that's going to be a really significant change in the way the graphics stuff's going. And what it's going to do is it's going to bring it into the same model as basically movie and television rendering, where you don't worry about, when you're writing a RenderMan shader for Pixar or something, you don't worry about the fact that, if I add one more texture here, it's going to stop, or it's going to give me a compiler error. It would be like writing a C program that on one computer can only take 4 parameters to a function, and on the other could take 8. I mean, that would be ridiculous, but that's the situation that we're in graphics right now. And while I think everybody's on board with high-level languages, Microsoft's got their stuff. We've got CG and the OpenGL 2 proposal from 3D Labs. And there's a lot of work going on here. And in truth, the differences between them just don't amount to much. I know there's going to be awful tactical syntax wars about this, about how some particular feature of, say, CG is better than some particular feature of the Stanford shading language or something like that. But in the end, it's really not that big of a deal. Any of them is a huge benefit over what we've got right now. So I feel that the industry recognizes that we need to move this high-level language for various reasons, but the virtualization aspect of it is not a one battle yet, and that's something that I'm still kind of campaigning for in a lot of ways. And there's, it's degenerating past even my normal level of technical discussion here, but I can go on forever about all the particular reasons about why it's a really good idea. But that's my point to keep hammering home on hardware vendors. And it's actually more of an API issue than a hardware issue, although there's hardware things that can help it out there. But once all this is going on, there is going to be a yet larger version of the offline and online rendering technologies. And this is one of the really kind of spectacular things that sometimes things come along where it really pleases me by having the industry evolve faster than I expected. And a couple of years ago, when it was first being talked about having floating point pixel formats and decomposing complex things, people would say that, yeah, we're going to have offline renders and stuff using this type of stuff. And it's obvious that it is going to happen. I mean, we've got the world kind of divided into a few camps there, where there are some people that, again, it's kind of amusing to watch. They're just like, oh, this will never happen. We'll never render a film movie with a 3D graphics accelerator because it's completely different operations. And they're really just wrong because They're looking at it from the space of like what you can do in a game engine, and the game engine has this specific number of little tweaks that you can make on it. You can turn this on, you can turn this off, you can replace this texture. And yeah, sure, you're not going to do a movie type operation like that. People aren't going to have the control that they want for something like that. But the point that they're missing is that all of these high-end renderers and everything, where you've got RenderMan or the built-in renders for the modeling tools, they're still basically just running computer programs that are doing adds and multiplies and rasterizing triangles if they're not ray tracers. And once we've got flexible operations and floating point pixel formats, the fact is you can decompose any algorithm into these sets of passes like that. And it's not just a matter of getting an approximation. You can make it do the same calculations. There's still usually trade-offs that you make where it'll be a better idea to set things up to take advantage of the strengths of the target that you're looking at. But you can do those calculations. It may take 500 passes or something, at which point the real-time people are like, 500 passes, what utility is that? That's ridiculous. They go off on their way. But the truth is, right now we've got, in Doom, there are probably a lot of scenes that, let's see, we've got 5 passes on a low-weight card, 5 passes per light per surface. Say we've got 2x real depth complexity and 2 lights on each surface. So already that's 20 rendering passes, which would be 30 textures being accessed per pixel, and then we may add 20 or 30 layers of shadow overdraw on top of all of that. So we're looking at maybe 50 passes. Now on some pixels we might have 100 passes or something going on there. Now we'll look at the pace of hardware evolution. A brand new card, like a brand new ATI card, is about 100 times faster than, say, the Rage Pro, which is our minimum spec machine for Quake 3. 100 times. You know, that's just a really significant advance here, and there's no reason to believe that we're not going to see similar advances in the graphics coming up over a comparable period of time from now on. It'll take long eventually, but I think we've got at least another 100x improvement coming at roughly the same speeds there. You know, we've got, so our bus bandwidths have quadrupled, and our clock rates have gone about a factor of 5, and then the hardware designers have just generally gotten cleverer by a factor of 2 to 4, so for how they use their resources. So we've got a bunch more of this coming on. So we say, all right, so we're doing 50 passes on something right now. What utility would 500 passes be? Then we can say, well, we'll be able to do that in a couple of years. It's just not that far off at all. I don't think next generation game engine technology is going to be built around 500 pass rendering, but the truth is, those are even kind of the rare cases on the Pixar level rendering. A lot of the shaders just don't take up all that much space. Some of the people that are working on them right now, that's another problem that I've got in fighting the virtualization battle is I've got people telling me, look, we're running movie quality shaders without having to virtualize all of this. It fits within our, whatever, it's 16 or 32 textures and 1,000 instructions or something, so why do we need to virtualize? But you know, there's just a little bit of hindsight there shows that that's not right, because we have the same people saying, like, well, whatever, 128 or 256 vertex registers is more than enough, and that's been a real problematic thing for a lot of people already. But the ability to go ahead and do this extremely complex rendering, literally movie operations, I mean, it's an overused term which I hesitate to even talk about there, where these people have been saying it since the introduction of like the GeForce One or something, and it's not really been true. It's been a matter of, you can produce some really nice pictures and you can set up some particular demos, but there's no way you can use the existing quality stuff to do movie rendering. There's just the fidelity differences is too large, the exact operations you need to do are too different. But that time really is coming to pass, where I expect, actually before the end of next year, that there will be commercial quality, at least television rendering done that's actually produced on 3D graphics cards. There's been a few things happening in the industry that have exceeded my expectations for adoption ratio on there, where I knew the hardware was coming, but the big conventional companies, the rendering code for something in Soft-Image, say, or RenderMan, they are really large code bases, and some of the code in there is literally 10 years old. They're not about to just go out and revamp the entire thing to take advantage of this new hardware. But what's going to be happening is there are a few smaller companies that are a little bit more nimble there that are going to be taking advantage of the hardware acceleration here, and they're going to be able to provide a benefit that's going to be really startling to people that work in offline rendering, where early on, it's not going to have every last little feature. You're going to be able to look at it and say, oh, I don't have the exact jitter grid subsample arrangement that I want, say. So picky little things at the end. But it's going to be something where instead of taking a half hour or 3 hours or something to do a rendering of a frame, it might be done in 10 seconds. It's not going to be a real-time operation still, but we're talking orders of magnitude improvement. And I think there's a good possibility that some of the old standby companies are really going to be hurt by this, that there's going to be a continual cling to their huge investment in their code base, the exact capabilities of what they can do. But there's going to be these smaller companies coming along that are delivering these just huge demonstrable benefits there. Maybe not handling absolutely everything, maybe not having exactly the same quality in edge cases, but being able to throw stuff out that much faster. And it's also surprising how many of the picky things can just go away when you throw more results at it. Like if you want an exact rendering that's exactly specifying your jitter subsamples across a bunch of different grids, well, you can get more or less that same effect by just rendering a scene with 10 times as many pixels and picking which ones you want out of that. And that becomes still maybe 10 times faster or more than doing it all in software. And the analogy that's going to start becoming painfully evident to a lot of people is the old supercomputer market, where some big crazy supercomputers and various vector processors like that, at one time they were the only way to go because they were the fastest computers with the largest memories and the fastest I/O and all that. But they've been on a decline for a long time, and right now they're really only used for a few very small specialized applications in some of the fluid dynamics and crash simulations and things like that. Because you wound up having microprocessor-based systems come along, and at the start people would be like, oh, these are toys. You can't use them for real work. And those are, in fact, those are great words that you'll see in the representation about graphics and rendering now, toys and real work. And those people sat there and they kept doing their real work on their multi-million-dollar machines. And then people started building up the different things necessary with microprocessors. A lot of them really weren't all that good. But the rate of growth there started accelerating more and more, and to the point where even the old jobs that used to be done all in the vector processors are now almost always done on microprocessors. The microprocessors are actually faster at almost everything except for these massive memory bandwidth-bound things. So the same thing's going to happen with rendering, where you'll have the people that are doing their specialized ray tracing work, where for some things ray tracing really is about the only way to get exactly the effects that you need. And you'll have products that are produced or films that are produced that showcase this exact way of doing perfect caustic specular reflections or something that's like a high-end render or ray tracer type feature. And they'll have spent billions of dollars on a render farm, and it'll take their designers this 6-hour cycle between the time they make something, they want to see how it looks, and the time they get something back to look at and say, oh, that's not really what I wanted, let's make a change and try it again. And then you'll have real-time crowd, which is looking at things where, okay, it's still triangle rasterized and things worked on the cube maps and projected onto there, and it's not really exactly what you want from a photon tracing standpoint. But you're going to have things which produce, RenderMan right now, all the Pixar stuff is not a ray tracer. It's effectively a scanline rasterizer, the way you do hardware acceleration there. I mean, there are more advanced renderers, but there's no reason why you can't do literally no edges or anything, Pixar quality rendering on the upcoming hardware accelerators. So that's going to be coming, and you're going to have the designers having the option about seeing the things actually in real time, where even if they are these 500 pass shader stuff, if you want to look at the character and all the lights in the world and set up like that, that's going to be running at game speeds without an environment behind it. And then even when you throw everything into there, you're going to be able to render low resolution scenes at interactive speeds, 5 frames per second or something, with everything that's actually going to show up in the movie. And then when you go ahead and make your final rendering, you just go ahead and crank up all of the options, render huge resolution, get good anti-aliasing going on it, all that. And that takes tens of seconds to go ahead and render something like that at gigantic resolutions. So that's also going to have a really good deep feedback into the game side of things. It's been obvious for a while with their version that we're able to take, like in Fred's case, he went directly from working on Shrek to working on Doom, and the skills translated very well. And a few years before that, as we were getting to 32-bit color, we were finally able to take kind of conventional artists that are used to that working with real colors and working on games instead of working in 2d6 color depaint stuff. So, and it's also happening now with models at the new level where you go ahead and build a model that would be suitable for a movie, go ahead and work in there. But what's going to be happening, the next step is with the generalization of programming languages and the capabilities of new hardware, the types of things that technical directors do at the film studio house is about getting exactly what the designers want from the lighting and surface interactions. That level of skill will also be directly applicable to the games. And it's going to be almost a no-brainer that anytime somebody creates content for something that would be non-interactive, computer graphics thing, some kind of TV or film show, you're going to really be able to use much of that content directly for interactive applications. And that's important because it is very much a case that media creation is the dominant factor in doing really high-quality games right now. And we have many times more artists and level designers than we have programmers, and we've got more programmers now than we've ever had before. And the ratio is probably going to continue to grow. Some companies are much more lopsided that way. There are certainly projects that have many dozens, or in some cases, over 100 content people working on this. And that does start to have some real impacts about what you can attempt in your game designs on there, where if you need to employ 100 artists to do something, it starts becoming a really dicey proposition about how much money needs to be put up for it, how long it's going to take everyone to do that. And being able to share some of that load between other ways to use the media and use the time there is going to be beneficial for the companies that go that direction. id Software is never likely to become a gigantic media house. It's just not what we do, not really the directions that we want to see the company go in. But lots of companies will be taking that route about, we've got all these capabilities, let's really use them. And it's going to be exciting to watch that type of stuff. I wouldn't necessarily want to run a company like that because it's going to be so risky to have that much labor going into something where you're just really crossing your fingers and hoping that it sells well enough to pay everybody. But what it's going to allow is, some of the things that make it do, it's actually a good point that a lot of the design decisions have been things that try to minimize the labor, because we have hired more people than we've ever had on a project before. We've brought in a lot of people with beef up talent in different areas. But a lot of the game design decisions from a technology standpoint have been things that attempt to reduce that, to try and make the tools interactive, to try and not require massive artist presentation on every single surface. We get a lot of mileage by being able to have, say, one bump map that looks different in different places with the different lights on there. But something that I'm looking forward to seeing, that I'm looking forward to somebody else doing rather than us, is having a team that goes in and actually creates a world with Doom-level technology, but uses enough art resources to paint every single surface uniquely with that. And that level of uniqueness is going to be a dramatic step over what we've got now. There have been a few examples of cases where you've been able to make really uniquely textured areas, and they look just dramatically better when you've got an artist that works over something. They labor over one room for weeks, and it looks just absolutely glorious. And it would be wonderful to see an entire world decked out like that, but it would be a different type of game that it would either be incredibly expensive to produce, or it would have to be a different type of game. We've already made some of the motions where Doom is slowed down in pace from our games previously. And there's probably going to be some level of backlash against that, where Quake was slower than the original Doom, and a lot of people hated it, and the new Doom is going to be slower than Quake, and a lot of people will hate that too. But it lets us get a lot more mileage out of the content that we've got. It just wouldn't be right to have somebody zipping by all of this work at 90 miles an hour. It's not the type of game it is. But it is useful to recognize from an industry standpoint that the zip around type game, something that's more or less Quake 3 about the technology, it's great. That's basically a solved problem. designing expansive world, lots of characters that run around and interact there. A game designer doesn't have to sweat that level of technology much anymore. The performance that we get out of Quake 3 level stuff now, of course, it's just ludicrous where you're seeing these 1600 by 1200 runs at 160 frames per second. What a game designer who didn't want to use next generation technology would do with them, of course, is go ahead and bump up all the content levels, where you just go ahead and use higher polygon models and this and that. Although the great thing that you really want to do with that is add more unique objects. And that's one thing where you look around the world and say, what part of this would be cool in a game or would not be possible in a game engine? And right now, like looking out over several hundred people here, like this scene could not be rendered in a game engine at a reasonable speed because it's tons and tons of objects and things aren't balanced for that so much. But that is an interesting direction. And there's been a few titles that are taking some of that in an interesting way. But being able to create as a game designer there and not worry about absolutely hitting the best media, you've got a lot of freedom now because the technology has evolved to the point where you really can concentrate on your game design and not have to worry so much about being absolutely latest and greatest, taking maximum advantage of all the technology, because things have been made easy for us. And again, that's the old grouchy programmers will complain about how things could be done so much more efficiently and all that, but they kind of missed the point about. The point is for the game designers to be able to make an interesting game, and throwing technology and hardware at a problem there is a really good solution. I mean, all told, it's a hell of a lot better to maybe just move your target along with Moore's Law and have an easier time rather than necessarily sweating as hard as you always used to on there and getting more features thrown into the game. Doom's got a lot of stuff thrown into it right now, and we've got more programmers than ever working on that. And we are intentionally pushing a lot of the different technical areas on it. But I'm looking forward to seeing what our licensees do with the technology, where they're kind of relieved of the burden of nailing down and advancing the technology, and they can go ahead and really make it, take it as a tool with the artists. And we've always been impressed when we see the first stuff that comes from our licensees when we're just still kind of learning how to do all the different things appropriately in the game. And there's going to be different paths which we're not pursuing either because we decided against the route, we didn't even think about it. And the first year or so after Doom's release, there's going to be a lot of exciting things happening from other people experimenting around and trying things there. But the total content creation thing is something that there's going to be some really spectacular looking things done like that when we take this level of technology and give an artist the time to paint everything, go ahead and lay down absolutely everything, and that will be just breathtakingly beautiful stuff in there. We'll have some scenes like that in Doom, but because it is still a first-person shooter, we have a certain amount of anchorage that we're kind of obligated to provide there, where it just wouldn't be the right thing to have a game that only took 3 hours to play through for your $50. But it'll be interesting to see what games that are targeted more for us, an area where you don't need that much acreage, where one thing that's been tossed around several times on previous licensee stuff is doing something that's kind of, it's even back to the old 7PS model. If you model one house and you model it really, really well, and that type of thing will be exciting to see in Doom level technology on there. But the kind of leading together of film rendering with the games is going to be exciting there. Where one of the things that I used to point out was some of the scenes in The Matrix that used computer graphics rendering on there. Some of the best looking stuff in there was really just large texture maps. There wasn't any clever RenderMan level pixel shading stuff going on. Like some of the subway scenes that were used computer rendering on there were just great big texture maps on really simple models. And you can literally get that level of quality right now out of existing game engines even, no matter just throwing enough kind of media data at it. Which does bring me to my the one thing that I've been championing for the last couple of years that was on my big hit list that I have not gotten in the mainstream cards is virtualized texture memory. 3D Labs is the only company doing that. And I've got a great I told you so right now where ATI has been working on their driver and doing all this. And their position, which was, had some merit to it with previous situations, was that we don't need virtual texture memory because we just fill our texture allocations with eGPU we don't swap textures. Because what people would notice on, say, NVIDIA hardware, which concentrated on maximum peak performance, is you have to swap big textures in and out. So when you've got a 1 megabyte texture, you turn a corner and you see 1 pixel of it, it swaps the whole megabyte in and causes a little noticeable pitch. While leaving things in HEP is a reasonable approach there, on previous generation cards, it went a small amount slower, but it didn't have any big hitches. But as we've got to the hardware now, where we've got 256-bit DDR memories on the cards there, the difference between pulling a texture from HEP and texturing locally is a really big difference. And ATI made some pretty significant speed-ups recently, just managing their texture memory better on there. But it's still a matter of there's clearly not an optimal way of doing it. But once we virtualize the texture memory there, then it just kind of all works itself out. You get little hardware bubbles as you're swapping stuff around, but the granularity is really important. And hopefully that battles one, because it's a few other fronts where some of the other, the offline rendering people have been throwing the same message there, where just swapping texture, you need virtualized texture memory. And it's not a matter of you need a few tens of megabytes of it. You need gigabytes of virtualized texture memory. That's absolutely going to be happening, where you're looking at gigs and gigs of texture data slapped around various real-time rendered worlds. And the hardware just needs very minor changes to get that going, and that's definitely going to be showing up. But then you do just get back to the content creation problem, where it can take an immense amount of time to go ahead and create hardware or to create content to go ahead and be used in that situation. The synthesis will always come out of the wall at this point and say, well, we'll do something to simulate all of this stuff. And I've historically been not a believer in that approach. There's lots of interesting stuff you can do. It's like, here's a cloud, here's a mountain or something like that. But a good way of looking at it is synthesis. Basically, procedural effects, or whether it's textures or models or whatever, is just a really limited form of compression. You have the idea of what you really want to get, and then you fiddle around with all the parameters and try and get a procedural model to produce what you want. And it's always, sometimes it's enlightening and you get things that are like, you're just twiddling knobs and like, hey, this is really cool, and that's great. But in the case of a lot of places where you're trying to just synthesize something because you don't have the time to paint it all, say, you're almost always going to have been better off if an artist did have the time to go through and put paint on every single little thing. Hybrid tools are going to be a good evolution to things like that, where you start having paint maps, which are kind of directing procedural evolution. And it's been interesting to see that even Pixar has sort of come along to that level of things, where they used to be some of the high defenders of synthesis, where you could synthesize anything in a rendering shader, but so much more of the production work now is just dealing with massive amounts of directed textures. And you still use interesting things like you paint, say, a bird's eye view of an entire island, and then the texture shader goes in and looks at that and says, okay, well, this green pixel I'm going to expand by combining all of these other like moss textures or whatever there. But it still winds up being data-driven, and you need people with artistic eyes, and we're not going to get away from needing lots of artists, and better and more capable artists, as we get more capabilities here on the rendering side. Certainly one thing that we've seen on the content side with Doom is that, well, we've really been seeing this since the evolution of all the last Quake games. There's been the kind of transitions of necessary skills, where in the early days, all that we needed to do was know about the gameplay and maybe have some sense of rough proportions, that doors shouldn't be too skinny, ceilings shouldn't be too low. That was about the extent of the aesthetic sense that was necessary in the early days. But as we got more and more capabilities, we just started really running into kind of people's individual limits on what they could produce usefully there, until you get to the point that you're giving them 10 times as many polygons to new features, and things don't really look all that much better. And that can be a little depressing as a programmer for a while, where you're like, okay, all this extra work is just not making that much difference. And then you see a really talented artist get at that, and you can tell that they've been held back previously by the limitations of the other games. And when you see that their skills have been able to kind of blossom into the whole new capabilities that you've got, that's when you really see the benefits of advancing the technology, why it's worthwhile to keep pushing the rendering technology like this. Doom's come together, I think, showcasing a lot of that. And being first generation is not going to show all the best benefits of it,
But this style of thing, the basic paradigm that Dune has of lights, projected lights, exact shadows, lights as first-class entities, the consistency between all of that, I really think that this is going to be the paradigm for most of the gaming industry for the next 5 years or so, like light maps and vertex-shaded characters have been for the previous 5 or 6 years. So I've got pretty good ideas where I'm going with next generation technology. And at the moment, I'm a little bit torn between some of the things where, for the most part, my work on Doom, significant contribution to it, is done, set in stone. The render decisions are all made. We're adding a few minor tweaks here and there, like I have to add some controls for sorting different levels of shadows with non-self shadow tweaks. It's that level of kind of tweaking and then a bunch of optimization that's left to do. And I'm getting a little tempted now to start peeling off and working on some next generation kind of technology demonstrations to research some of the things. And some of those might possibly wind up in the shipping Doom engine. Like we separated them in Quake 3 where we had core features and we had some things that were considered novelties. And in some like the earlier GL Quakes, like we would have, in the original GL Quake, we had mirror rendering, which was not intended to be part of the game, but it was a rendering novelty. And in Quake 3 we had, the basic sort of stencil shadow case on there, which we didn't expect people to play with. It was a novelty. And we might wind up with a couple of those things in Doom. There's some stuff that I'm kind of excited to be trying with the new generation hardware capabilities. But once Doom's done, I think the plan is that I will be working on new rendering technology. So there may be less of a gap between full generational steps than there was previously. But the nice thing is that the content creation process won't change too much. It was a big change going from the Quake series to Doom because level designers needed to think about lights, not just as kind of brightening areas up, but as real first-class entities, and the whole move to normal maps for the artists. There was a lot of learning to be done there. But it's likely that the next generation rendering technology is going to use exactly the same media that we use for Doom, for the same basic things about normal maps, diffuse maps, specular maps. We may add a few more additional things there, like a shininess map or a couple other parameters that we may want to add to things like that. But there's a good chance that the same basic way you build content isn't going to change even for next generation rendering technology. And the way you put levels together right now could probably be used for commercial quality offline rendering. If you plug this type of content into much better quality renderers that take care of much more details. It's a little early to say whether, like, what importance indirect lighting will play in some of these things, but those are the research questions that I need to answer. And I've got a bunch of other things with solving a lot of the analytically intractable problems that we currently got, like soft shadowing or motion blur, ways of tying all that together. So there's still interesting things to be done, but perhaps the most interesting aspect of that is that there's a real chance that the next generation rendering engine will be something that's a stable, mature technology that lasts in more or less its basic form for a long time. Where, again, we take the example of RenderMan from Pixar. That really hasn't changed much. The core language specification hasn't changed much in over 10 years. And people have gone from making your first little Luxo Junior type animations to rendering Monsters Incorporated and all that, where huge, massive changes without changing the structure of the way you go about building it. Lots more data, more offline tools, more things that tie into it, but the core structure stayed the same. And there's the enticing possibility that the next generation game engine, rendering technology, may wind up like that. It's certainly possible that there will be an intermediate step where lots of lessons will be learned. There will be the one after that that lasts for a decade. But we're definitely closing in on that level there. And that should be a good thing for the industry all around. I mean, it's a little bit less things for, in some degrees it's less exciting for hardcore techie programmers to not be able to not have good reason to go ahead and write new engines all the time. I mean, people will continue to do that because it's kind of fun, but the justification will be a lot lower for that. And a lot of these graphics programmers will move from being engine programmers to being technical directors in the Pixar style, where you're much more helping the artists create the effects that they want, because the core tools are all there. It's just a matter of acting as the interface between algorithms and a designer's mind. So That's about all I've got for this, so I'll take questions as long as anybody wants to. Maybe the lights turn down a little bit, I can't see hands.